Welcome to everybody who is joining us for tonight's meeting, either on Zoom or YouTube or, well, anywhere else really. We're back online this week because the access up to the mills is still not really clear. They are working on it, and Leisure and Culture tell me that they are hoping that this will be declared open within a few days. So hopefully the mills will be back functioning quite soon. Leisure and Culture have decided, I think wisely, to maintain the restrictions that they've had of 12 people wearing masks as a maximum at the mills. And, you know, for an outfit that need to make public announcements of it's on, it's off, it's open, it's not, that's probably the sensible thing. And given we have only one other guest speaker and then our AGM, we're going to do the same because it's just not been terribly reliable recently. So David will be sending out links for the next two meetings. So our next meeting's on the 11th of March, which is our last guest speaker. And just one other thing, which is Jim Barber is going to put together a newsletter for us again. So if anybody has anything they want to send in, be it informative or just funny or whatever, send contributions into Jim and he'll collate the newsletter for us. So we can move on to tonight's guest speaker. Hopefully things have settled down, who is Kenneth Duncan from the Royal Observatory at Edinburgh, where he's currently on a Marie Curie Fellowship. And tonight he is going to tell us about the Weave project, which is an instrument which is being installed in the William Herschel Telescope in Las Palma, and clearly has many features and functions, which I'm sure he'll be able to tell us about. But one of them is that this project allows the telescope to have a field of view of 2 degrees, which increases its observation and measurements of up to 1,000 stars per hour, which in itself is just staggering. So I am really looking forward to hearing about this project. And also he's going to tell us about the progress that's being made in the measurements that this is allowing us to take. So over to our guest speaker, Kenneth, for this evening.
Hello, yeah, and yeah, hopefully the noise is gone. I realized, yeah, I did have YouTube open in a tab that was buried from testing earlier that obviously had gone live in the background, and I was getting everything in duplicate. Right, let's try. Let's try again. Right. So here we go.
Can we get everybody else to mute so we don't get interruptions?
Okay, yeah, so if you want to give me a thumbs up, you can still hear me and everything, see everything okay? Oh, yeah, crack on. So yeah, thank you very much for the invite, and yeah, sorry if I caused some confusion with the noise there. I thought I'd start by introducing myself and kind of a little bit of my career path. So I sort of started with a physics degree at Durham University, not really with a sort of particular lifelong passion for astronomy. You know, I was interested, but it wasn't really the sort of reason for going, or specific reason for going into to do physics and astronomy at Durham. But it was sort of while there that I did find a sort of a passion and interest, and I think also some aptitude at doing the research that took me on to doing a PhD at the University of Nottingham between 2011 and 2015, working mostly with data from the Hubble Space Telescope on some of the sort of very first galaxies in the universe. And from that, I moved abroad to the Netherlands, so Leiden Observatory, which is one of Europe's sort of biggest astronomy departments. I went to work there for 4 years before moving back here to Edinburgh in 2019. Initially on what was sort of called as a joint Leiden-Edinburgh Astronomy Fellowship, before then being awarded a European Union Marie Curie Fellowship that I've been on for the last year and a half. So my general research, and I think I describe myself very much as an observational astronomer, and that's working with a whole range of observational data sets to study galaxy formation in a number of different ways. And generally, my sort of approach is what is a sort of growing approach within the field, which is to do large-scale statistical studies of these populations, because we need to use these big population studies in order to understand the sort of the subtle effects and how the physical processes that drive the large-scale evolution of both the galaxies or stars in the same way. So generally, I'm looking at answering questions such as, how and when did the first galaxies form? How did the first supermassive black holes form? And then how those two are kind of interlinked. So, how is the accretion and the sort of the feedback from supermassive black holes shaped the galaxies in which they live? And on a sort of more day-to-day technical level, a lot of my sort of work life is trying to answer the question of how far away is that galaxy? In worryingly ever-increasing samples to recently, my paper that's about to go out, which is estimates to approximately 1 billion galaxies. And those numbers are only going up with future surveys. Thankfully, Weave is not going to do that much. But I thought I'd better also do a little bit of background just to make sure that sort of everyone was on the same footing. When I talk about observational astronomy and the research I'm doing with these big statistical samples, generally it all falls into sort of two primary camps. Either we're working with photometry, where we're taking images of the sky in a given sort of wavelength filter, and actually potentially ideally building up multiple combinations of these different filters that span the electromagnetic spectrum to build up a general picture of large numbers of sources. So this is a nice illustration of a nice spiral galaxy going from ultraviolet through to the infrared, and you can see that the different wavelengths pick out different features within the galaxy because they're probing different physical processes or stars of different ages, etc. And the benefit of photometry is that, as I'm sure most of you are more than familiar with, you can point a telescope in the sky and you get to see lots at once. And particularly when you've got images from things like Hubble, and you can see here the classic Hubble Ultra Deep Field, you can get hundreds of thousands of galaxies within a small patch of sky. And with the latest generations of photometric surveys, it is running up to these billions of sources that I talked about that let us probe huge numbers of sources for different reasons, but it also let us probe some of the kind of the rarest and the most extreme things where you do need to look through the needle in that haystack. The downside of photometry is it doesn't include that much information for an individual source. So the second family is really spectroscopy, where you take that light, we split it up with either a prism or a grating or some combination of the two, split the light up into its constituent components so that we can see the really detailed chemical features, so the emission lines and the absorption features that correspond to the elements that make up the stars and the galaxies we're looking at and the gas around them. So you can see here the emission line features in optical for a number of the common species that we look at, and you can see that it's these unique fingerprints that give us information about what elements and what sort of molecules are in these parts of the sky. And sort of within the galaxy, but more generally, this is a sort of nice sort of simple picture of the various combinations in that can either come from the emission lines. So you've got some ionizing photons that excite some gas, and you have these electronic transitions. And then when those transitions produce the corresponding emission lines, those transitions give you the corresponding features in emission. So you can see the sort of bottom left emission line spectrum, or you see them missing from the continuum light to give you those same different fingerprints. And depending on what type of eruption you're looking at, whether it's gas or the stars or things in sort of the intervening medium, whether it's emission or absorption sort of will depend on what you're looking at, but those same features are the key things we care about. And the reason why spectroscopy gives us extra information on top of photometry is that it gives us access to not just what elements are in there, but it gives us velocity information. The sort of widely known Doppler effect. The source is moving away from us. It's shifted towards redder wavelengths, redder light. If it's moving towards us, we've got bluer light. So this is just an illustration of a sort of rotating system where the star is wobbling to and from, and you can see the variation in the spectrum. But this holds more generally to distant galaxies where the expansion of the universe takes over and those galaxies are receding away from us, and it stretches the light and gives us the redshift effect. And spectroscopy lets us measure that distance. We know from the current cosmological picture that if we have a redshift, we can turn that into a distance that takes the observational information we have and lets us turn that into a sort of intrinsic physical property. So this is why spectroscopy is really valuable, because you can get a really detailed picture by comparing the patterns we see to what we expect it to be from the laboratory rest frame. So this is great in that we can get a huge amount of information from an individual galaxy or star. And traditionally in astronomy research, this has come under a number of ways, and the classic and the simplest one is performing long slit spectroscopy, where you take your field of view and you kind of block everything apart from a long slit, along which you then disperse the light through your prism or diffraction grating to get your spectrum. So one of the nice things about long slits is that you have a sort of a spatial direction. So you can see going kind of top to bottom along that sort of mock galaxy, you get a spectrum at every sort of slice down, and you can spread that out. So you can also see more than just sort of one piece of information for that source. But if it's resolved, you can get additional bits of information and look at how it's varying across a given source. But then this is slow because you can only look at one galaxy or one star at a time. So a sort of a second approach to this is sort of just doing that multiple times. So taking your field of view and then blocking everything, but you machine out some holes. So this is typically done by manually machining aluminium out on a plate at sort of every point down where you've got a source that you want to make a spectrum for. You kind of machine out a small slit, and then you get at the corresponding part of your spectrograph, once you've spread the light out, you can get a spectrum for every one of those sources. And this is much more efficient and can get you sort of tens to hundreds of sources. But there's a downside in that you can't have these slits overlapping, because there's a potential that the spectrum end up merging on the detector that you're kind of putting them onto. So there's a sort of a limit as to how much you could put on one plate. And this is why kind of in the last couple of decades, there's been a move for a lot of these surveys to what is now known commonly as fiber spectroscopy. So rather than blocking out all the light apart from the bits you care about, you just collect the light only in the places on the field of view that contains the star or the galaxy you want to look at. So you place your fibers over the field of view of the telescope, collect the light in that circle, and then because it's going into a fiber optic cable, you can make that fiber optic cable as long as you want and wind it around, and you can then kind of layer them up and make them efficiently kind of produce spectra onto your CCD in sort of arbitrary orders and arbitrary positions to make sure, well, within some reason, you can't put them right next to each other on the sky, but you can then much more efficiently target all these sources. The downside of this is that you've obviously lost some of that spatial information. You're collecting all the light and you're just collecting it together and saying, this is the sort of the sum total of the light. But if you're looking at a star and these are unresolved and we're doing that no matter what, and then if we're looking at more distant galaxies, once we get to the distant universe, the majority of these are sort of what we'd say is unresolved, and you're collecting that all the light anyway. So the sacrifice isn't as severe once we're looking at more distant galaxies. And then for stars, there's no sacrifice at all. So it's all gain from that perspective. But yeah, there's a question of how you then do this. So I talked about, you place these fibers, and the most sort of famous survey that's done this so far is the Sloan Digital Sky Survey. And the way they do it is they have a sort of hybrid approach where they've got these plates and they've drilled out the holes where the sources are, and then they have to go in by hand, and you can see the video on the right, manually plug in these fibers into the plate so that the fiber optic cable is in the right part of the sky. Can I start that again? There you go. And it works in, Sloan Digital Sky Survey is sort of transformed the way we do a lot of modern astronomy by getting us millions of spectra for stars and galaxies over the last 20 years now. But this is an extremely time-consuming process, and it requires a lot of manual labor. That means that there's only so much you can do with that approach. And because you're using these aluminium plates, it's still sort of using up resources. You're having these are a one-time thing, which is why if you go to lots of places, they give these away to institutes and individuals and organizations, because they can only be used once, and they're then just a nice demonstration or an outreach tool. So there must be a better way. And obviously the title of my talk is clearly giving it away, but there is now this sort of new generation of spectrographs. So the one on the top left here is the dark energy spectroscopy instrument, which is now sort of taken the lead and is already operational. It's in the US. The foremost is an instrument in the south that's going to go online in a couple of years. And MOONS is an instrument that's being built here in Edinburgh to go on the Very Large Telescope. But the one that's most close and dear to my heart is an instrument called WEAVE. So WEAVE is an acronym, and we do love acronyms in astronomy, is the WHT, Enhanced Area Velocity Explorer. And in like classic modern astronomy fashion, it's a double nested acronym. So WHT is then the William Herschel Telescope, which is a 4.2 meter telescope in the Canary Islands in Palma. And you can see it sort of pretty much labeled. And I think it is exactly, if you can lean in, that tiny white spot. And this is a telescope that's operated by the Isaac Newton Group, which is a collaboration between the UK, Netherlands, and Spain, which runs this. And just a little bit down the road from this one is the slightly smaller Isaac Newton Telescope. So WEAVE is a sort of next generation spectrograph that's being built, and I'll go into a bit more detail of what it can do and how it's sort of being put together. But just to summarize, and it was mentioned in the introduction, so this is a telescope now that has a huge field of view, and this is part of the upgrade to the William Herschel Telescope. It's this 2-degree diameter area of the sky that it can see because of this new corrector lens. And then we have 1,000 fibers, or close to 1,000 fibers, that are positioned automatically by robots. And that gives us huge improvement in the number of sources we can do this for. And what's also big improvement on things like SDSS in the past is that we've got an increased coverage of wavelength and an increased resolution. So that enables much more precise measurements of things like these velocities of these stars, or the chemical measurements, and more precise understanding of what's going on when we have those spectra. Sorry. So the WEAVE itself is sort of a very complex piece of equipment. And as an observer rather than an instrument builder, I've developed a lot of this knowledge sort of by osmosis within the project over the last 4 to 5 years. But there's a couple of nice sort of simulations, and WEAVE as a whole actually encompasses a lot of this stuff. So the big telescope, so the telescope itself is unchanged and has been as it is for the last few decades. What has changed largely is the stuff that's going at the top. So there's this sort of big chunk of equipment that you'll see kind of in a bit more detail later, that's got this new prime focus corrector lens and this robotic fiber positioner that all ties in together, and then loops the fiber cables down on the side into this spectrograph room that lies on the side. And this is really impressive piece of kit. and it starts at the very top where you've got this prime focus correct lens, which is these set of lenses that have been added to give it this really huge field of view, the largest of which, the sort of labeled L1, is over a meter in diameter, and is extremely expensive piece of glass. And you can see sort of a couple of the various stages of its construction and testing and polishing on the images on the right. But this is just one of many lenses that are in place to fix the sort of the various aberrations and kind of aspherical things to make sure that when it reaches the fibers, there's the very flat field of view, so that when we place the fibers on the part of the sky, we're expecting to see the source, that it is where we think it is. And there's also crucial aspects to make sure that as you're observing through the night, when the telescope's moving, that you're minimizing the effect of all these optical effects so that the light from your source doesn't move off the fibers across the whole field of view, and that everything stays where it's supposed to be. So the lens is extremely impressive, and it ends up as part of this sort of bigger lens structure that you can see at the left. So you can kind of see it in full scale. And this has been mounted on the telescope itself, so you can see it in place on the right. So it's mounted at the prime focus of the telescope, and then on the back of it, what you can see here is basically a dummy weight that is sort of sitting in place of where the robotic fiber positioner will very soon be. And that's the weight is necessary because of the really sort of delicate balance within the telescope, because I think this whole the lens and the robotic positioner are several tons. So if you don't have that weight in place, then the balance at the bottom of the telescope and the motion of the telescope as it's moving around the dome is going to be severely out of whack. So it's really useful to make sure that everything's kind of set in place. So I think there's some kind of quiet noise that I think I can talk over, but this is a press video that was put out. But it's not even kind of widely released. It's just available on the Emission Group's website. So the first 30 seconds or so is just the outside of the dome. Actually, I think I can skip ahead. Yeah, there you go. So you can see a little bit. Probably better. The interior of the new control room that's been upgraded to help improve the automation of the telescope, and that sort of big box replaces what was some very clanky 1970s equipment. But this is then just some nicer views of it in place, and the sort of the broader context of where that lens sits in the telescope, and the scale of the spectrograph rooms and the whole scale of the instrument. So you can see, that's the bottom of the mirror, and then this is sort of the outside of one of the spectrograph rooms with the various ventilation ducts to make sure that everything remains at the correct operating temperatures. So it's very impressive, but this is still just a corrector lens, and all it does at the moment is produce a very nice sort of wide field pretty image. And there's some test data that produces a nice pretty image, but what we want is the spectra, and this is where this really cool robotic fiber positioner comes in. So I'll try and sort of talk through the engineering picture on the left to sort of put a bit more of it in context before you see the real thing. The interesting stuff, and that where the sort of the light hits, is what's labeled here as sort of field plate A. So if you can kind of, that sort of the gray circle is an aluminium plate, which is the field of view of the telescope, and around it are a lot of these fiber attractors. And the sort of the extremely neat part of Weave is that there's sort of two sides of it. So the bit at the top is where the robots are positioning fibers for the next observation. But while all that's going on, the bottom of it is the one that's facing the sort of the field of view of the telescope. So it's observing one set of configurations, on the bottom. And then while the robot is on the top, kind of moving the fibers around, and I'll show you in a sec what that looks like. In order so that once you finish one set of observations, you swing the thing around and then it goes straight on to the next set of observations and then starts the next configuration, so that there's very little downtime. So not only can we observe 1,000 between those sort of 1,000 targets, we can use very little downtime and really observe efficiently throughout the night. So the top right, you can see a sort of graphical representation of what these configured plates look like. So their sort of fibers are poured in from the edge by these robots and placed on the field of view where they need to be. And I've sort of done up a little cartoon of what this sort of looks like in profile of these little buttons. So there's a small little glass lens that is attached to a little magnetic sort of I don't know what to call it, button thing that has sort of robot can lift from the little thing at the top, and I think you get a better view in a second, and pull it out to where it needs to be. And the fiber optic cable is on a sort of retractor that makes sure that it sort of goes out smoothly and gets pulled back in. And then those fibers are sort of taken away around the side down to this cable wrap that's at the bottom, sort of pulls out to the side, round the sort of the top end of the telescope and down into the spectrograph itself.
Now,
so Gavin, so I'll start again. So these are pictures of the sort of the robotic position in construction in Oxford. So you can see kind of the top left. Actually, it's better to look at the video. It's much more fun. So you can see the little sort of aluminium bits with the magnetic attachment on the bottom, and the robots come along, pull it out, and you can see there's sort of 3 layers. So they can cross. They can sort of the fibers on the upper layers can cross over the others, so that we can make sure that we can see as much of the field of view as possible, and that we don't snap a fiber when we're trying to drag another one out, because what we really don't want to do at any point is have the robot clash with one of those fiber optic cables, because they'll snap and that's that fiber gone for good. And there is an expectation that some will break, but it's all very carefully designed so that the robot knows where these fibers are and knows sort of the safe ways to move it. So you can see it going through a kind of couple of safe steps, and this is it very much doing its sort of first toddler steps of testing to make sure once the fibers are in. But once you've got the whole thing in place, so I talked about the whole thing rotating. This is a little bit of the inside of what that looks like. If you can imagine the plate being on the top of this, the whole machinery rotates within the box very slowly. Let's zoom it up a little bit, So you can see, it's a couple of minutes, but it's still extremely quick to move on from one observation to the next. So during this period, obviously the telescope can be moving to point at the new set of targets to sort of the new sort of central position. And then by the time it gets there, everything's rotated into place and it's sort of ready, you can acquire the guide stars and then start to do the next observations. And so these are just a couple of pictures of the machinery in place in the lab before it was coated. And so that's Ellen on the right, who was a PhD student in Oxford, who did a lot of the work in constructing those fibers. And for scale, Ellen is Dutch, so she's at least 6 foot, so you can kind of see it's a big piece of equipment. But it's really, this was the very key piece of work that made it all come together, was me very tentatively holding a fiber optic cable while Gavin, who designed and built this instrument, did the hard work. So this was at a meeting in Oxford in January 2020. And you can see between the last pictures and this one, the aluminium had been sort of taken off to be anodized and coated in black to minimize obviously any sort of kind of reflections and stray light. And this was then Gavin starting to put all these fiber attractors back into place. And yeah, an extremely fiddly job. And this is why I was just sort of holding a fiber optic cable to make sure it didn't bend and snap while he was trying to get the whole thing into place. While my main role is on the scientific side of things, I can at least sort of happily say I've helped to build the instrument, at least more so than some of the other people in the collaboration. So this is what it looked like, kind of in a bit more sort of reality. So all the retractors are then in place. You can see the full sort of 3 layers. And this is also being a little bit backlit. So you kind of look at the ends of the fiber optic cables, you can see a little bit of the light coming through just to help demonstrate. This is Gavin zooming in slightly, and you can see how complex these configurations are and how sort of careful the robots have to be to make sure that they don't clash. And it's sort of, this is moving at roughly half speed compared to what it will end up doing. But part of the reason why it's going slowly at this point is because the counterweights for the robot aren't installed. So because you've got these heavy robots and they weigh several kilos, if these are sliding along and trap your arm, there's a serious risk of injury. So what needs to happen is you need a counterweight to offset with that motion, because obviously you don't want the telescope or the focus to be kind of wobbling around as the robot's moving. This is just another angle so you can see a bit better again the different layers. So the counterweights are there to make sure things don't break. Although, ironically, it was the counterweights that broke during shipping to La Palma that cost us about several months. So there was a brief discussion about some of the impacts of COVID. There was a period where the positioner was shipped off and it sat in Liverpool docks for about 8 weeks without being moved when it shouldn't really have been. This was in, about a year and a bit ago. So last winter. And when it was shipped, it clearly wasn't the A team who were sort of manning the forklift truck, because something was dropped and the counterweights ended up like the bolt was sheared off, which requires a slightly worrying amount of force. Thankfully, the rest of the instrument was okay, and they fixed the issue with the counterweights. But this is one of those sort of 2020 hindsight of Gavin realizing he probably should have just removed the weights before shipping and put them back on. But it was supposed to be shipped with a bit more care than it ended up being shipped with. This is what it looks like once it's done. And like I said, the way it's all being designed is that configuration can happen in an hour, and then you swing the whole thing around, and you keep going with the next 1,000 targets. And because you've got then sort of 940 and 960 targets, and I'll explain the difference in a sec, you've got about 2,000 of these in total. And you've got, once you add up all the sort of the length of cable and the retractors, it's 117 kilometers in total of fiber optic cable inside Weave, which is amazing what Gavin and Ellen and others in Oxford have been able to do to put it together. So I sort of alluded to the slight difference. So there's a reason why one of the plates has slightly fewer fibers. It's because in addition to this sort of normal multi-object spectrographs, or what we call MOS mode, where we use the individual targets, what you can also do is bundle these fiber optic cables together into a kind of nice grid, so that you can get sort of different pixels effectively of a galaxy. And there's 20 of these, what we call mini integral field units, so mini IFUs. And those can also be placed around the field of view, so you can get a sort of resolved picture of an individual galaxy. And then we also have this other mode that's called the large IFU, which is sort of covers it's an arc minute and a half across in terms of its scale, so it's sort of significantly bigger. And you can therefore just stick that on a big galaxy. And the way that's useful is that if there is bad weather, so if the optical seeing is too poor for the small fibers, the large IFU has larger optical fibers, so it's less impacted. You lose less light, and it's also really quick to configure because you can just stick it right in the field of view. You don't have to worry about a configuration. So if there's been, say, a shutdown in the night because of bad weather, so clouds come in and you're restarting, you don't know exactly when the weather's going to clear and you want to observe and make the most of the light. So as soon as you can start observing, you stick the large IFU on whatever sort of backup target you've got, and then you can start configuring the other targets in the background so you've not lost any time. And the mini IFUs are also give you a sort of intermediate mode where they only take 20 minutes to configure, or even less potentially. So you've got ways to sort of really maximize the efficiency of the telescope. So this is everything now safely in place, and they've been doing various testing because it's all the machines have been tested at sort of at sea level in Oxford and at sort of at a fixed angle, and now that it can be put in place, they want to test how things sort of flex and how as you move around the sky, does everything kind of still stay sensible and the things not get too distorted. So this is all in place in La Palma now, and the final piece of the puzzle is the spectrograph, and this is where my ignorance really kicks in, because the spectrograph is extremely complicated and has required expertise from a large number of teams. But maybe the interesting part is that there's two sides. You've got a red and a blue side. So as the light comes in, you split the light with a dichroic, and you send the sort of the blue light to one spectrograph and the red light to another. And that's key because it means you can make the most of the photons that are coming into the telescope. Because when you're choosing how to split the light up with a spectrograph, it's often the balance between how much resolution you can get versus how much you're sort of splitting the light up, and the wavelengths that you can cover simultaneously. And this is where, by splitting the light up and doing things simultaneously, you can get full optical coverage with the really high resolution that we want. And this is, again, just more pictures in place. So I think on the right, you can see in full, it's the sort of the red spectrograph. And you can see also the size of the CCDs. So I think they're about sort of 6 by 9,000 each. And so for the blue and the red arms, you've got these two CCDs. So there is a gap, but the way the design is set up, you can put that gap in a sort of in a less important part of wavelength coverage. But they're particularly impressive, and it gives us really high resolution. And there's a lot of data every time the CCD is taken. And that's this is that part of the instrument being delivered and dropped into one of the spectrograph rooms. So you can see sort of the pieces of the puzzle are being brought together, but obviously we dealt with COVID, and the universe thought to just throw another thing in our way, and this was the eruption in La Palma that you'll have seen last autumn, which in the end didn't turn out to be quite as severe as we thought. So just to put this in context to show you, the blue is where the telescope is, and red was where the worst of the eruption was in La Palma. And you can see this is a picture of the smoke plume from the rim of the caldera just above where William Herschel Telescope sits. And thankfully, the prevailing winds mean that most of the dust and the ash was sort of, at least from an astronomical perspective, obviously the dust and the ash and the lava was extremely problematic to the island, including to many of the observatory staff. But from a telescope perspective, the damage and the risk to the telescopes was less severe because of the prevailing wind generally. And it seems like we've also done okay during the winter, because one of the other risks was the fact that there's been these mild earthquakes, and there's always a risk of landslips at the top of the mountain, which can block the road for access. And when you've got these earthquakes, and then winter kicks in, you get ice that sort of expands these cracks. So there was an increased risk of the access roads being blocked, and that more severely impacting things. But thankfully, after all these various teething problems, I mean, when I picked a date in September last year. I thought we would have data now, but it looks like we're going to be later in the summer before we have our official first light. But things are going smoothly, and I think there's a nice contingency to make sure that that date doesn't slip too much into the future. But obviously, yeah, we're crossing our fingers for no more COVID variants that limit travel, particularly when key people need to come back and forward, and for no more natural disasters. But anyway, so that's sort of where we're at with Weave, and this is then a sort of slightly more technical summary of what Weave can do. For those that you're interested, so telescope diameter is 4.2 meters, so that field of view, as mentioned, is pretty large. And we have these 1,000 fibers that have a 1.3 arc-second diameter. And the resolution that we can achieve with the spectrograph, so the wavelength step relative to the observing wavelength ranges from about 3 to 7,500 in what we call the low resolution mode. But there is then also a high resolution mode where within a couple of narrow windows, you can get resolutions that are between 13 and 25,000. So those are extremely high precision and are really there to let you get very high precision velocity measurements on bright stars. And that's where the resolution is really key. And the fact that we can then do that for 1,000 sources potentially is huge. When Weave does finally start taking photons and everything is running smoothly, Weave science is going to consist of a large number of programs. So what Weave is going to do, and this is where my work really kicks in, is start to perform a coordinated set of surveys that span 5 years. And this involves scientists from across the ING partners, so the Netherlands, UK, and Spain, but also a number of countries that bought into Weave to help fund it. So this includes France and Italy, as well as institutions in a number of other European countries. And the sort of broad headline goals cover a huge range of things from, what is the chemical and dynamical history of the Milky Way? So, when did the stars in our Milky Way form? And also where, because some of them might not have formed in the Milky Way and, could have come in from dwarf galaxies, and, how did that happen? Other questions like, how do clusters of galaxies themselves evolve, the sort of biggest structures in the universe? And then also trying to answer cosmology questions. So, what is the nature of dark energy? And these come under a number of surveys. So it's about 8 in total. And it seems maybe slightly imbalanced against the galaxy, but one of these on the left, the Galactic Archaeology Survey, as it's known, is significantly the largest. So in the galaxy side, there's these sort of 3 surveys that cover a huge different range of things. Within galactic archaeology, there's also lots of sub-surveys. And on the right, the extragalactic surveys, because of our love of acronyms, just gives you a whole bunch more acronyms. So Weavelofa, Weaveaperitif, and all these things. And the stellar populations at intermediate redshifts, or STEPS survey. And these are covering a different range of topics. But the one I'll sort of focus on, which is the one I'm most closely involved in, is a survey called Weavelofa. And this is a project that's sort of very, very UK led. So the lead of the team, so the science team lead, Dan Smith, is based at the University of Hertfordshire. And then I'm the deputy science team lead for this project. And we're sort of coordinating and working with over 60 astronomers across Europe, but with a lot of involvement, like I said, from the UK and also the Netherlands. So importantly, might come back to that. I think it's probably useful to explain what Lofar is first. And so being close to Edinburgh, you might have had talks in the past about Lofar, but it never hurts to have a refresher. So Lofar is it's the low frequency array. So it's a radio telescope based in the Netherlands, but now spanning almost the entire width of Europe, and a large fraction from north to south. So from Ireland in the west through to Latvia in the east, and the next sort of station to be built is down in Italy that increases the north-south baselines. But the core of the telescope is primarily like within the Netherlands, spanning kind of about 100 kilometers. And at the very center, which is the image you were seeing before, is the core of the radio telescope. And it's probably not like any radio telescope that you've seen before or seen in movies in your classic Jodie Foster and Contact. It's really just a bunch of receivers in the ground. And what makes Lofar both unique and difficult is the fact that it's a software telescope. So sort of slightly low resolution image, but these black squares are sort of protective shields around a bunch of radio dipoles. And the radio image is built from collecting the signals from all of these different receivers, both from within the Netherlands and potentially simultaneously from across Europe at these sort of remote stations, to build a radio image. And I think going into how we would do that isn't entirely the talk. It's involved some very interesting kind of developments in both the sort of the radio astronomy, but also in kind of computation and big developments in how we make use of high performance computing to do complex astrophysical calculations, because this requires the use of both Dutch and German national supercomputing facilities and the use of the Leiden and Hertfordshire sort of smaller high performance computing centers to produce these images. But the cool thing is that it all now works, and Lofar is doing a survey of the Northern Hemisphere with radio that is more sensitive and at higher resolution than has previously been possible on these scales. So this is an image from group led here in Edinburgh with Professor Philip Best. And this is our sort of deep field where we've gone to the same patch of sky over and over and over again. And this is one of the deepest ever radio images of the deep universe ever produced. And it's comparable with anything that existed before, but crucially between 5 and 10 times the field of view. And that's key for getting us these sort of rare and interesting sources. And you can see some of the spectacular examples of these weird and wonderful radio jets. But also gets us some of those most distant radio sources that have been seen in the universe yet. Alongside the sort of the deep field, there's this ongoing all sky survey, or a sort of all Northern Hemisphere survey. And I couldn't find a sort of a prettier image that showed the full scale, but this is just on the plane of the sky, the area that's been covered so far by the Lofar survey. And the first data release we had in 2019 was the sort of yellowy sort of stripe in the middle there, which at the time was Chris Evans, who plays Captain America in the Marvel films. Turns out he absolutely loved it, and he gave us a retweet, which counts really well to our sort of outreach numbers with his 10 million Twitter followers. So that was great fun. But actually today, very coincidentally, the area outlined in black, so that's our sort of second data release that covers, it's about 5,500 square degrees. So it's a quarter of the Northern Hemisphere in total, give or take. That was publicly released today to the wide community, and it's the largest ever radio survey. So 4.4 million radio sources, which we're talking about very big numbers again, and that's where Weave comes in. So just to back up a little bit again as to what we're seeing in Lofar, and I won't go into how these emission mechanisms work, but the key thing with the radio image is that it lets us detect active black holes. So accreting black holes produce these radio emission because they have these very powerful jets that produce relativistic electrons. And when those move in a magnetic field, you produce your radio emission. So you get these jets. And the really crucial thing is that because these jets are being seen in radio waves, they're not impacted by any sort of gas or dust in the intervening galaxy or the sort of intergalactic medium. So we're not, we can see obscured accretion that isn't observed at other wavelengths. And also crucially, you can see a spectacular image that's from the second data release of our Lofar survey. It's a nice supernova remnant, and the radio emission is in blue in this image. So this is one of the supernova remnants that shows up. And it's the same mechanism in that you have these supernova going off and you have these energetic particles that produce radio emission because they're moving through the magnetic field of the Milky Way. And if you've had recent star formation, you have then these supernovae going off within a few million years. So when you've got a lot of star formation, the collective signal from all these supernova remnants can produce a strong radio signal. And I'll scroll back a little bit. The top left image, you might wonder why there's a zoom in onto a very boring patch of sky. And it's because these are all actually, the vast majority of these little blobs are distant star-forming galaxies. And we must be vigorously forming a lot of stars simultaneously in order to produce the bright radio emission. But because the supernovae are much fainter than the AGN, it takes a lot of radio observations to get down to these sensitivities. But once you do, you get a huge number of these sources. So yeah, but then why do we need Weave? So we've got all these core radio sources, and I've sort of told you what they are, but we don't know that necessarily a priori. And the reason why we need Weave to combine with Lofar is because when that radio emission does come out, it sort of has a very simple form. So the synchrotron emission has basically, we describe it as having a power law. So as a function of the radio frequency, it follows a sort of very simple power law slope in intensity. That means that when we're looking at these distant galaxies, when it's redshifted and stretched by the expansion of the universe, you just end up with something that looks pretty much the same. So if all you're then seeing is the dark green line, you've no idea, when you're comparing one to another, is that one further away? Or is it just at the same distance, but it's fainter? And particularly when we're looking at things like the star-forming galaxies, is it forming one solar mass of stars per year, or is it much further away and forming 100 solar masses of stars per year? Like, that's an important question that the radio alone just can't give us. But this is where Weave comes in, because by then taking a large number of these radio sources and getting the spectroscopy, the optical light from those host galaxies gives us that precise information. So you can see an example of a couple of sort of radio sources on the right, and you have that combination of the continuum emission from the stars, and then all the key absorption and emission line features that let us really accurately say it's exactly this distance away. And once we know how far away it is, we can turn that radio emission into a kind of an intrinsic jet signal that tells us a lot about what's going on in that black hole. And more crucially as well, and these spectra illustrate it, is it tells us a lot about the mechanisms of how that black hole accretion is going on. And we think there are different ways that this goes on, and they produce different signals because both of these spectra on the right are from very bright radio sources, but you can see the host galaxies have very different features. One seems to be living in the bottom. The bottom one is a sort of what we call a very red and dead passive galaxy with no strong emission lines, while the other is got these strong emission lines that suggest there's much more extreme activity and sort of something powering these nebulae. And this is where the spectroscopy is really key, because not only do we get these distance measurements, but we get really good statistics on a huge range of parameter space to find out basically, what is powering these radio sources? How is this evolving of a cosmic history? So the goal then for this survey is combining the Lofar and Weave data in this Weavelofa survey, trace how a black hole how a black hole has grown across cosmic history, and the numbers, the samples we get from Weave are really crucial, because we can study enough of the radio sources to find like the rarest and the most extreme. So potentially the most distant, some of the first active black holes. And it also gives us the large number statistics to kind of probe much more subtle trends in how these things have evolved, and get access to information about the questions I raised earlier of how the black holes have impacted their host galaxies. So it's really it's one of those cases where it's greater than the sum of the parts, and that Weave alone could never have identify these galaxies or identify these black holes, because the radio was needed, but the radio alone could never have also then told us all this other crucial information. So I think in terms of time, I can come back to it if we want, but given that I've sort of had most of my time, I'll just sort of leave a summary and that just advertise more generally. There's a huge range of these new facilities coming on board, and I listed a few of them earlier, but there's more in the future that cover different science cases and different telescopes. And this is going to really revolutionize what we do, because it's going to take spectroscopy into the tens of millions of sources. And we've provided nothing else goes wrong. And actually, I needed to update the date here. This is what I get for reusing slides. We're in early 2022 and the science has not yet started. But we're going to be getting science soon. And you can see just while I showed that the radio data was being produced by Tim and Philip, we're not all softly spoken white British guys. It's a very big and diverse team that's producing the science. And this is from a Weave team meeting in Naples a few years ago. And if you squint, you can see me sort of roughly in the top left, popping my head in. But yeah, I hope I've interested you with the excitement, exciting science we're going to try and do with Weave. And yeah, hopefully you'll invite me back in a year or so to see some of that real data and the kind of discoveries and the science we're doing with it. So thank you very much.
Thank you. Thank you.
Oh, Kenneth, thank you ever so much. That is just remarkable. I mean, it's remarkable in just about every sense. The engineering, the resolution, the potential data. It's a phenomenal project. It must be fun to work on, actually.
I mean, yes. I mean, on the whole, yes. But as we're all humans, so when you get a team this big with different competing priorities, there are certain days when it's you tear your hair out. But I think when we start seeing data,
be a part of, though. Yeah,
exactly.
Phenomenal. Gosh, well, one thing for sure, we would be delighted to have you back in a year with the data from this. That will be just remarkable to hear you back with that. So we need to keep a tab on where you've got to in a year from now. Yeah. How are we doing with questions, David?
Yeah, we've got a few coming. I think there's another one just popped in. No, it's just messages saying thank you for an excellent talk. I've got about half a dozen questions from Zoom and YouTube. Scully Brooks is asking a couple. Can the fiber optic glass, would it alter the spectrum in any way, both on yours or on the Sloan Digital survey?
Yes, it will, sort of. In the chromatic aberrations come in at the transition between the different media, right? So when you go from air to glass, you have the different refraction indices, which is why the lenses need to be careful. So you minimize that by making sure that sort of at the point that the light is coming into the fiber optic cable, everything's sort of as parallel as possible, so that it hits the fiber optic cable to collect the light as sort of parallel as possible. And then once it's in the glass, it doesn't really matter what journey it's taking within the glass. There's no chromatic kind of or color issues. You then but it's about making sure that all the light is properly collimated, and that's within both the prime focus lens and I think key parts of the spectrograph. It's really about making sure that the light kind of stays coherent once it's out of the fiber. But I think once you're in the fiber, it can kind of bend in weird and wonderful ways as long as it stays within the glass and there's no cracks. I think you're safe.
Cool, yeah. Also another question from Scully about the fibers, saying they're very thin. Would thicker fibers give you more light? Or is it a matter of getting them to fit in?
So it's a balance, yeah. I mean, you're right. The more glass you have, the more light you collect. But then you also have, and it maybe ties back to the previous question, that they're less flexible, right? There's only so much you can bend the fiber optic cable. So if you have a thicker one, you can't bend it as much. But actually, the more scientific reason for making them that big is that it's a balance, because when you're taking a spectrum of the source, you want to get as much of the light from the star or the galaxy but with as little of the background as possible. And I'm sure kind of a lot of you are familiar with this in terms of like minimizing your kind of sky background. If you make your fiber too big, you're just going to get more background light that starts to give you lower signal noise in the source you're looking at. So there's a balance between getting as much of the signal as possible, particularly given the optics and the sort of the blurriness, the seeing above La Palma, to get as much of that as possible without getting too much background. But then you've got a sacrifice of, if you make it too small, you lose some light, and particularly if you've got a nearby galaxy, and this is the downside of the fiber optics, is that if you've got a nearby galaxy, you don't see all of it. You just get a chunk, and we have to be careful about how we correct for that in our observations or in our sort of analysis. But it is a balance, and it depends on the science case. So yeah, good question.
Yeah, Phil's got a question about the fibers which cross over each other. Are they touching at the points where they cross over?
Good question. I guess potentially, but not with much force. So starting with the videos. So there's a lot of rules. So I talked about, the robots need to know where to put them. There's a very part of what my role is, and is getting from a catalog of things you want to look at to sort of the instructions to the robot of where to put the fibers. And thankfully, a lot of the hard work has been done by one of the engineering teams at Rutherford Appleton Laboratories in kind of down south, who's written a piece of code that makes sure that nothing crosses. So when it's working out where it can put targets, it calculates for those targets all the potential collisions, and then there's a sort of a zone of avoidance around each target. So once a fiber is down, there's a sort of region where you can't put it. And I suspect it's probably down to very small margin. I don't know whether currently we're being kind of safe and making sure they're not touching, but we'll kind of be a bit more optimistic in future. But generally, I'm not 100% sure. So I can ask Gavin next time we have a call whether they are allowed to touch, because it does look like some of them get very close. But they're being put down with sort of micron precision. So it wouldn't surprise me if they're close, but they never touch to within some hair's breadth, literally.
Right, that probably relates to the next question, which was what is the positioning tolerance? But if it's micron level, then kind of answers that. But how often are the positioning robots checked and calibrated?
So that will be a constant act, really. So a lot of the effort, so like I said, everything's at the telescope. So in principle, you could kind of go, right, we'll bosh it all together and start taking photons. But what's going on now is doing a lot of that really detailed checks of running, and while other things being going on, the telescope is busy sort of night after night doing kind of mock tests to sort of run it through and just do sort of failure operations and see how long it goes. So every time the instrument is taken off the telescope, which we hope is not much, but under the current agreements, there are other instruments that could go back on the telescope for the community to use. We're hoping they all want to use Weave for the 30% of time that isn't already taken up by these 5 surveys, but it could get taken off. And then every time it gets put back on, there'll be a very kind of strict set of tests and calibrations. And that's something actually we're organizing now, is sort of exactly which targets we want to look at on Sky to make sure that everything kind of works correctly. But I think the robots themselves will be monitored nightly to make sure that everything's running smoothly.
And again, related to the fibers, what is the field of view per fiber for each fiber?
So the fiber diameters for the multi-object spectrograph is 1.3 arc seconds.
Right.
So by the time, sort of in my head, kind of a distant galaxy about Redshift 1, sort of most of the way back in the universe, ends up they're going to be of order an arc second across. Some of these things beyond, and the seeing at La Palma ends up being sort of yeah, on the very best nights, you'll get, I think it's like 0.4 arc seconds. You know, if you've got a star, you know, the very best optical conditions, you'll get a spread of about 0.4 arc seconds. And for our own observations, actually for Weavelofa, we have a requirement that we don't observe anything worse than 1 arc second, because if we do, we lose too much light, because the galaxies are being blurred too much and we lose some of the light. But there are other targets. So for the bright stars, they don't care so much, so they can observe in in worse conditions, and that's why it's all kind of like interleaved together, so that when it's dark skies, really good conditions, the difficult galaxies are done, and when it's sort of bright skies or poorer seeing conditions, then you swap to the targets that best suit it, because if you lose 20% of your flux or 50%, they're so bright, you still get the signal.
Yeah, that sounds good. Yeah, we've got one question on the Lofar side of it, which is the circular island, the Netherlands
Yes,
telescope set up. What is the scale of that? Because there isn't much to give you an idea of scale there. So how big are the receivers and things?
A few hundred meters across. So I didn't get to say one of my favorite Dutch words. This is the superturp. It's called the Lofar superturp, but the superturp is a sort of an old Dutch word. Basically, it's a slightly raised patch of land within the sort of marshes, so that when the floods were higher, the townspeople could retreat to the slightly higher land. And this is there's a reason why Lofar is based in this part of the Netherlands, because it's very sparsely populated and even more sort of marshy than normal. So that's the superturp here. I think it's of order a kilometer for this bit, but there are, and you can just about see in the top right maybe. There's there are dishes that are sort of scattered a little bit further, and then you go to the remote stations that are from kind of 1 to 10 kilometers away up to 100 kilometers away, that sort of gradually spread out. But this is just the very core of it, where the dishes are most tightly packed. Yeah.
Okay, and related to the radio thing again, the question is, how does a higher intensity result in a lower frequency in your plot of the intensity frequency graph? That kind of
this is okay. So yeah, maybe I should kind of go into this a bit more. So this is if we were to be able to observe every frequency. Yeah. So from higher frequencies on the right, if we kind of could keep observing the same target at all these different frequencies, you'd see the intensity a given frequency increase as you go to lower and lower frequencies. So this is say one target. So, and you can observe that, and it's the same, if you go across, it's equivalent to, looking in wavelength as a function of wavelength, how bright is the optical galaxy. This is in radio as a function of frequency, how bright it is. And it just follows this sort of simple power law in intensity, so that for a given radio frequency, what the next intensity is going to be. So this is for one target. This is what the spectral slope looks like, and that means that when it is stretched, we just get something that looks very similar. Hopefully that makes a bit more sense.
Yeah, it does. Yeah. I'll maybe get Phil to unmute if he's okay doing that, to ask the question about active galactic nuclei, because I'm not sure I can properly parse it into.
Yeah, that's okay. Yeah, I'm just wondering if with these various spectroscopy measurements, you can find out anything more about the theories of unified, what an AGN is actually, depending on what your observing angle is. It could be a blazar, it could be a Seyfert type 1 or type 2 galaxy. I'm just wondering if these spectroscopic measurements will actually shed any light, because there's quite a debate at the moment over unified AGN theory, isn't there?
No, exactly, and that's one of the key reasons of getting the spectra is, like I said, with these classifications, we'll get, I didn't show it here, but within the radio sources, we'll get lots of quasars, we'll get lots of sort of very classic kind of radio galaxies in sort of big red dead ellipticals. And what often prevents us from getting a kind of concrete answer on those unification theory questions is you end up just seeing one type of population and the other, and it's sort of these biases. You're not comparing apples with apples every time because they come from different surveys and different ways of picking them out. And so when you're trying to compare these data sets, you don't know. Whereas because one of the ways we've approached it with Weavelofa is we're just targeting all of the radio sources above a certain brightness in these different different levels, so that we get a complete picture of the radio population, regardless of the other selection criteria. So that means that when we have these classifications in these redshifts, we can then bring in the sizes and the jets and look at the morphologies and kind of answer those questions without being worried that we're biased between these different samples. So I think, yeah, we may not be able to solve it because it's been running for decades and it clearly isn't a sort of open and shut case, but Weavelofa is definitely going to be one of the data sets that lets us do this over the coming years, because it gives us such a complete picture of all the AGN activity, and we get the extra information to be really crystal clear about, you know, what kind of source is powering it in a way that hasn't really been possible with previous surveys, just because of the way that they've gone about picking their targets.
Thank you.
Right, I think that's kind of all the questions from the YouTube and Zoom chat. So unless
Could I
anybody
just
else...
ask, you did mention about repeat coverage of the sky. I mean, how much repeat coverage do you think you might be able to get?
Yeah, so it varies depending on where we're looking. So
Yeah,
this is our current deepest image, and this is 180 hours, and it's sort of done in 10-hour blocks. So this is 18 views passes with Lofar, but since this was released a year and a bit ago, we've been taking data, and in the next month or two, we'll have our sort of our full depth image, which is 500 hours. So it's sort of 50 observations. It's going to go even deeper than what we've got. And the way we're doing this with Weave is sort of the same approach, where, you know, we've got parts of the sky we've looked at repeatedly in Lofar. We're going to go back to them repeatedly with Weave as well. So because we've got so many more targets, I'd say about a third of our kind of spectroscopy is going to come in. There's 4 fields in total that are like this one here. That's called, like, it's the Elias North 1 field. We're going to come back to these 4 sort of smaller fields of view for about a third of the telescope time. And then over the sort of all sky stuff that I showed here, I think in total, we're going to aim to get about 6.5, ideally sort of 8,000 square degrees, but we're only going to kind of visit these once and just pick out the brightest targets, because, you know, the brighter ones are rarer. So we're going to look at the brightest ones over kind of the full sky, and then get huge amounts of statistics on these kind of fainter ones in the deep fields by coming back again and again as they come through in the sky. So part of the reason we have 4 is that they're sort of spread as much as we can across the sort of spring, summer. So it's from about 10 hours is one end, and about 18 hours in right ascension is the sort of the other one that covers us the sort of spring, summer season.
gosh, yeah, there's a huge amount. Yeah, thank you. How are we doing, David?
Just one last thing related to the thing when we were asking about the fibers and the size of the field of view and that. You don't do any atmospheric correction on this, do you? Because it's saying the atmosphere limiting the size of what you can look at depending on seeing and other conditions. So you don't do any corrections to improve seeing or anything?
No, so we won't use adaptive optics. And I think adaptive optics with spectroscopy is still kind of very much in its infancy. I think, yeah, there is instruments in, so the Muse instrument on the Very Large Telescope in Chile has it's only just recently commissioned its mode. But it's a good point in that we do have to be really careful, because these things will vary. But this is the way we do our data is sort of carefully selected so we can try and correct for this. So we know, stars are always going to be point sources. So we know, if we have a reference star where we know for sure, and and this is where kind of well-known bright reference stars are key calibrators. We'll have 10 white dwarfs in every field, where we know really well they kind of are fully characterized. We know exactly how bright they should be, so that whatever flux we're losing, whatever light we're losing because of bad conditions, we can correct for that. And then we know that correction, then we can apply it to the galaxies where we maybe didn't know, we wouldn't have known a priori what we've lost. So it's really important to correct for that, but we can't yet do sort of adaptive optics to minimize that. And I think because it's fiber spectroscopy, the benefits will be, because of our resolution, the benefits will be minimal because once you've got all the fiber inside, once you've got all the light in the fiber, you're losing the spatial information. Where it does matter is for these integral field units, and that's where this MUSE instrument in Chile is really key. Is that they're an integral, they've got a sort of image in the field of view, and you've got the spectra. So by improving the resolution, you get the spatial resolution too, and that's where it's really important. But no, I mean, it would be nice. I think it would make our lives a little bit easier, but probably be slightly higher running costs with running 5 lasers simultaneously.
All right, I think that's all the questions that are being sent in at the moment. Thanks.
Well, I can only thank you. I mean, certainly for the clarity with which you have presented your talk tonight. It's a complex project, and it is that was just so clearly done. That was wonderful. And also, what a stunning project. So we wish you the very, very best with that, and try to keep in touch so that we can hear how the data comes out, because that's not so far away now.
No, it's very exciting.
Love to. Yeah.
So I skipped some slides about the sort of galactic science, but hopefully I can come back and give you a nice an overview of all the discoveries we're making, not just in Weavelofa, but in some of the really cool stuff with the Milky Way, because there's going to be really high impact science there. Sort of the oldest stars in the Milky Way, new discoveries of tidal streams around the Milky Way, and sort of there's going to be really cool stuff across the science that I'm excited that I get to join in on, even when it's not my area, because of the sort of the way we all collaborate together.
You have one huge amount of data coming in.
Tell me about it.
Right,
Absolutely. Kenneth, thank you a million. That really was an exciting talk. That was great to hear. Just great to hear.
Yeah.
All the best.
Thanks for having me.
No problem at all. Thank you a lot.
Bye
now.
And some messages saying thanks very much, and it was brilliant from YouTube as well. So everybody's got a lot out of that.
Excellent. Yeah.
Thanks a lot, everyone.
Thank you now. Thank you now.
I'll just